So we have, welcome back, we have the inverse of a matrix where we have an n by n, so it's got to be square. Matrix is invertible if there exists a matrix C such that C times A equals our identity matrix and A times C equals our identity matrix. It's slightly difficult to see. Let me rewrote this. So we have an invertible matrix if we have the existence of this matrix C such that when you multiply on the right and on the left, you end up with your identity matrix. We write it as A with a superscript, -1. It's another way that we write that, and this is our inverse of our matrix A. If we have a matrix that's not invertible, we call it singular, and if it is invertible, we call it non-singular, just to have more vocabulary. And we're going to end up with just like a long string of things that all mean the same thing. It's going to be very exciting. A 2 by 2 matrix is pretty straightforward to get what the inverse is, provided that this AD minus BC business is non-zero, because that would give us division by 0, and we can't do that. That's undefined, so we just don't have that. But if we do have this is non-zero, then we know that our matrix A, our 2 by 2 matrix A, is invertible, and we can say that our inverse is this, which is 1 over this AD minus BC, which is called the determinant. More on that later. It's very exciting, but the determinant has to do with that. So we have our inverse of A is 1 over AD minus BC times this rearranged matrix where we're swapping our diagonals. So A swaps with D, and then B and C stay the same places, but they get negated. So that's that. And if we do have this AD minus BC equals 0, or our determinant equals 0, then our matrix A is not invertible, aka singular. To put that into practice, let's find our inverse of A. So first let's check if this is indeed invertible. So we have AD minus BC, so we have 3 times 6 is 18 minus 20, and that's not 0, so we're happy about that, and that's -2, so we have 1 over -2 times our matrix 6, -4, -5, 3, where we swapped our 3 and our 6, we swapped those and we negated the B and C values. And then we can just scalar multiply to simplify this out a little bit more, so we end up with what, -3. That was really loud. +2, 5 halves, and -3 halves. I need to stop my computer from giving me notifications. That was terrifying. Alright, hopefully I had muted that for you all. So there's our inverse of our matrix A. We can verify that it is indeed our inverse, just to check for like good measure. And how can we check that? We just multiply on the right and on the left, but we're just going to be lazy and just do one side. 5, 6, multiply on, I guess, the right. -3, 2, 5 halves, -3 halves. And what do we end up with? -3 times 3 is -9, plus 20 over 2 is 10, so that's a 1. 2 times 3 is 6, plus 4 times -3 halves is -6, so that's a 0. 2 times 5 is 10, minus 6 times -3 halves is -10. No, that's 9. No, wait. Oh no. 2 times 5 is 10, minus 6 times 3 halves is 18. We did something wrong. I'm doing this entry. Whoops. Okay. so that's going to be a 1. And then we have negative 3 times 5. Negative 3 times 5 is 15, plus 6 times 5 halves. So that's 15 minus 30 over 2, which is 0. So we ended up with our identity matrix, and it's very good. So we have, I guess, shown by this example that this works. Invertible n by n matrix. So for our matrix A, that it has an inverse, that it is non-singular. Then for each b in our Rn space, the equation ax equals b has a unique solution, and we know exactly what that unique solution is because you just multiply on the left with your A inverse. So this is like if you have a x equals b, and then you multiply by A inverse, then A times A inverse is going to give you your identity matrix times x, and that's going to be A inverse b. So that leaves us with x is A inverse times b. And I should give these all little hats. There you go. First, matrix A from example 2, which was this. We can use this to solve our system here by just finding x equals A inverse times b. So what is that? That's 3, 2, 5 halves, negative 3 halves, times our b, which is 3, 7. So pause the video, crunch that out, and let's see if we agree. We get 3 times 3 is 9, plus 14 is 23, and then 3 times 5 halves is 15 halves, minus 21 halves, and so we end up with, what, 23, 6 halves, which is 3. So our solution is x equals 23, 3, and we can check that by plugging it in. So 23, oh wait, this is a negative 3. So we can plug that in, so we get 23 minus, something went awry. Hang on. Forgot it's negative. So negative 9 plus 14 is 5, and that's better. Okay, so we end up with 5. This is why I highly encourage doing math with friends, because people can check your work as you're going along. So we have negative 3, and so let's plug that into x1 and x2 here, just to see if that makes true equation. So we end up with, what, 15 minus 12 equals 3, so that works. And then we end up with 25 minus 18, which is 7. Cool. So we did it. We found our solution to this system using our inverse. So if we have an invertible matrix, then that inverse is invertible. Like, wild. Well, that's actually pretty cool, because then if you take the inverse of your inverse, then you get out your original function. Or not your original function, your original matrix. If you have invertible matrices, then you can take the inverse of their product, and that's the product of their inverses in reverse order, similar to our transpose, where we had AB transpose is B transpose times A transpose, so like that's pretty cool. And if you're looking at your inverses transpose, or your transposes inverse, those are the same. So that's it's pretty cool. And that so that there's a lot of things that we can do with invertible matrices. We have the product of n by n matrices is invertible if those two matrices are invertible. So like A and B, that product is invertible, and the inverse is their inverses in reverse order, like that, which we had up there. So elementary matrices where it's just a single row operation on an identity matrix, an I with some number in it that gives you a n by n identity matrix, so I sub n. And it's a single row operation on that, so that could be a swap, that could be a scalar. Elementary matrices are just a single row operation on your identity matrix, or adding a row to another one. So these are all elementary matrices. This is taking -4 of row 1 and adding it to, this is taking -4 of our row 3. And then this is swapping our row 1 and row 2. And this is scaling our row 3 up by 5. So yeah, these are all elementary matrices. This one is taking -1 times row 1 and then adding it to row 3. That's where that is. And so if you do that on A, what is going to happen? So for E1 times A, what are we going to get? We're going to end up with our first 2 rows are untouched. And then our last row is going to be -4 times our first row. So that's, and then adding it to our third row. So you have G minus 4A, H minus 4B, and I minus 4C. So that's going to be that product. And E2 times A is going to give us a swap where we have row 1 and row 2 are switching, so we have D, E, F, A, B, C, and then last row is untouched, E, H, G, H, I, and then E3 times A is just changing our third row to scale it up by 5, so we have A, B, C, D, E, and F, but then 5G, 5H, and 5I. So that's what's happening. Note that we are multiplying the elementary matrix on the left. So multiply elementary matrix times A, where the elementary matrix is on the left of the matrix A. Matrix we're not doing a lot. And so if we have our elementary row operations performed on our matrix m by n from having some elementary matrix multiplied by A, then you can use the same operation where you're making your elementary matrix using that same operation on your identity matrix. Well, that elementary matrix is invertible because there's just a simple row operation that's happening, or an elementary operation that's happening to it, and the inverse of it, or what gets it back to our identity matrix, is just the inverse of that elementary matrix is the same thing that takes your elementary matrix back to identity matrix. So here, what would take this elementary matrix with its multiplication back to our identity matrix, so E sub 1 inverse is going to be, we just need to add 4 here, and then everything else we're going to keep the same. So we got zeros there. It's pretty cool. We have an n by n matrix that's invertible, if and only if. So we got an if and only if. It's pretty nice. If we have our matrix A is row equivalent to our identity matrix of the proper dimensions, and whatever elementary row operations get A to our identity matrix, also take our identity matrix to our inverse. So what does that mean? Well, if you set up your matrix A and you augment it with your identity matrix, and you do row operations for a while, however many you need to do, to get your identity matrix on the left side, then what you have on the right is going to be your inverse, as long as you did all your arithmetic correctly, which is, that's pretty cool. It's, and this works for any n by n matrix, so we're no longer limited to just 2 by 2, where we're looking at 1 over the determinant of your matrix, and then you multiply that by what, like d, a, negative b, negative c, like that, because that was pretty limiting. But now, you know, we can find our inverses of our non-singular matrices by performing row operations with a super kind of augmented matrix with our identity matrix. So I think I told you this, but there is an algorithm for finding a inverse where you row reduce your augmented matrix AI, and then you get I on the left, and then that you have your inverse A inverse on the right. And if you can't get your identity matrix on the left, remember it was an if and only if, that then you don't have an inverse. And now this is a really bad joke. Are you ready? I hope you are. And if you're not, pause the video and come back when you're ready. Why are math teachers all good at dancing? Because they algorithm. All got rhythm. Algorithm. It's pretty bad. Alright. Let's do that. What did we have? We have our matrix A, 0, 1, 2, 1, 0, 3, 4, negative 3, that's a 3, 8. And then our identity matrix, 0, 1, 0, 0, 0, 1. And then let's do some row ops. So what should we do? Well, let's swap so we get 1, 0, 3, 0, 1, 0, 0, 1, 2, 1, 0, 0, and 4, negative 3, 8, 0, 0, 1. What should we do next? We should probably eliminate that 4. So what do we get? Actually, this is going to make this really long. Here, let me pause this. Do it, and then we'll see if we agree. Row 1 times negative 4 plus row 3. Okay. Next, probably we need to take out this negative 3. That was row 2 times 3 plus row 3, swapped into row 3. Now, should probably divide out. So we get rid of this 2, or we get this 2 down to a 1, and then we'll back substitute or push it up. So row 3 minus row 2 into row 2, and then dividing row 3 by 2 everywhere. And let's finish it out. Matrix on the left, and then this is our inverse of A on the right. Looking at matrix inversion is thinking about our row reduction in terms of simultaneous solutions to our systems, where we have a bunch of different systems that are all set up to be equal to, like AX equals each of our columns of our identity matrix. And then you solve all of those all at once. And it's pretty cool because if you're only looking at finding a couple columns of your inverse, then you don't have to do all of it. It's kind of nice that you just have to solve a couple of them. So it's just working efficiently. And a numerical note that we seldom practically compute A inverse, especially when we have gigantic matrices. Just finding the inverse of them is a lot. Unless you need those entries. Otherwise, you can look at the row reduction, and it might just be better. Also, backslash on MATLAB works very nicely. That's like it's kind of like division, kind of, but we don't really have matrix division, but it is backslash so that you can do like A backslash B, and that will give you a solution. Just about does it for inverses of matrices. We looked at elementary matrices, doing our super augmented matrix in order to find our inverse. We got some properties. The inverse of your inverse is your original. The transpose kind of order flop happens. You can use your matrix inverse to solve equations, and we thought about the word determinant, but we didn't look at it too much because we'll think about that more later. And also our vocabulary where we have an invertible matrix is called non-singular, and a not invertible matrix is called singular. So fun. All right. Bye.